Welcome back to Practical PyTorch. One decorator can give a real speed up, but it wins on the right model and loses on the wrong one. Let's find its rules. Torch.compile fuses many ops into a few for a real speed up, and it has rules about what it can capture. It is not magic. On a real model it wins, on a tiny one it loses. We will measure both honestly. Compile captures your model's ops into a graph. Then it fuses them into fewer, bigger kernels. That cuts kernel launches and the memory traffic between ops. That is where the speedup comes from when there is enough to fuse. One decorator, real speedup, real rules. We measure both the win and the loss. This video has 3 parts. First, what compile does. It captures the ops into a graph, then fuses them. Second, the measured reality on a real GPU. Faster on a real model, slower on a tiny one, and why. Third, graph breaks. These are the things that split the capture and cost you the fusion. Part 1. What torch.compile does. By default, PyTorch runs eager. Each op runs the moment you call it. This first node is a conv. Next, a batch norm. It runs as its own separate kernel launch. Then a relu. That is 3 ops so far, 3 separate launches. A second conv starts the pattern over. Another batch norm follows it. And a final relu. 6 ops here, conv bn relu, conv bn relu. This arrow passes data to the next op, but each of the 6 launches pays the same fixed toll from the launch overhead lesson. Eager runs op by op. 6 ops, 6 launches, 6 times the toll. Torch.compile traces the same 6 ops and captures them into one graph. This box marks the region it traces. All 6 ops now live inside that one box as a single captured graph. Compile fuses their work into fewer, bigger kernels. The launch toll is paid a handful of times, not 6. Capture draws a box around the ops and fuses them into fewer, bigger kernels. That means fewer launches and fewer round trips to memory. That is the speedup, when the box holds enough to fuse. It is one line. Model equals torch.compile of model, wrapping the model in place. The first call is the one that actually compiles. It traces the model and generates code, a one-off cost we measure in part 2. Every call after that runs the compiled, fused graph and is fast. One line wraps the model. The first call pays the compile cost, the rest run fast. Part 2. The measured reality. Same decorator, 2 models on a real GPU. On ResNet 50, eager takes 619 milliseconds. Compiled takes 490, 1.26 times faster, with a graph break 504. On the tiny SmallCNN, eager takes 1.46 milliseconds. Compiled takes 1.9, that is 0.77 times slower. And broken, 2.47. The win is real when there is enough work to fuse. So ResNet 50 gains 1.26 times, but the same decorator on a compute trivial model can lose. SmallCNN drops to 0.77 times. Compile is a tool, not magic. SmallCNN on 32 by 32 images is compute trivial. Each op is a sliver of work, so fusing it saves almost nothing. Meanwhile, compile adds real overhead. It runs per call guards and dispatch to check the inputs still match the captured graph. And on tiny tensors, its generated kernels do not beat the ones eager already calls. Add it up. The overhead outweighs the tiny fusion gain, so compile is slower. There is a tempting wrong conclusion here. It helped on ResNet 50, so it must always help. No. On a trivial model, the fusion win is near zero, but the overhead is not, so compile ends up slower. Mixed precision had the same shape. It pays off on real-sized work. Almost nothing to gain from fusing, plus per call guard overhead. That is why compile loses on tiny models. The first compiled call is slow because it does real work. A Dynamo trace, then AOTAutograd, then inductor code generation. Measured here, ResNet 50's first call took about 53.5 seconds. SmallCNN's took about 8 seconds. These are one-off costs. Contrast the steady-state step. ResNet 50 490 milliseconds, SmallCNN 1.9 milliseconds. Timing that first call and concluding compile is slower is the classic mistake. The compile cost is paid once, so amortize it and measure steady state. That is exactly what the honest timing lesson was built to enforce. Part 3. Graph breaks. Some code the compiler cannot trace into the graph. An item call returns a plain Python number. A print of a tensor is a Python side effect, and a data-dependent branch like an if on a tensor sum needs a concrete value. The compiler hits one of these, gives up, and stops the graph there. One more honest note. An item call, or an if on a tensor, also forces a GPU to host sync at runtime, but the break itself is a trace-time decision. An item call, a print, or a data-dependent branch can't be traced, so the capture stops. Drop that item call into the middle of the captured chain. This new node is the item call, sitting mid-chain. A red break seam appears right here. It marks where the value must return to Python. The capture must stop at that point. At the break, the one captured graph splits into two subgraphs. This first box holds the ops before the break. This second box holds the ops after it. Each subgraph still fuses inside itself. And the item call sits in the gap between them, running as plain, eager Python. Nothing fuses across that seam. So the more breaks, the more of the win you lose. Same two models, now with an item call in forward. That forces one graph break each, and the item call also does its own small work. SmallCNN's compiled step goes from 1.9 to 2.47 milliseconds, a clear jump. ResNet 50 goes from 490 to 504 milliseconds, a small slip. Both had exactly one graph break. On a big model, one break costs a little. ResNet 50 slips from 490 to 504 milliseconds. On a tiny model, it hurts more in relative terms. SmallCNN goes 1.9 to 2.47. Even broken, ResNet 50's 504 still beats Eager's 619. The more the capture fragments, the more you lose. Quick check before we move on. You put a print of X in the middle of a compiled forward. What happens to the speed-up torch.compile was giving you pause and predict. It forces a graph break. The captured region splits in two. Eager Python runs at the seam and nothing fuses across it. So you lose part of the win, and how much depends on how badly the graph fragments. An item call, or data-dependent control flow, does the same. The full reasoning is in the course answers file, section 3.9. Torch.compile captures many ops and fuses them into fewer, bigger kernels. That means fewer launches and less memory traffic. The speedup is real on a real model, ResNet 50, 1.26 times. But a tiny model can be slower, 0.77 times. Fusing only pays when there is work to fuse. The first call is a one-off compile cost. Amortize it and measure steady state. and a print, an item call, or data-dependent control flow breaks the capture. That costs you the fusion. This is the one lesson in the course with a shelf life. Torch.compile moves fast, so its behavior and exact numbers are version specific. Everything here was measured on Torch 2.12 with CUDA 13. Treat the figures as a snapshot. The shape of the lesson holds. Capture and fuse. The win on a real model, the loss on a tiny one. The one-off cost and graph breaks, but the exact milliseconds will drift. So remeasure on your own version with the honest method before trusting a number. The numbers are a snapshot of one Torch version. The method carries over, so remeasure yours. You have now seen what PyTorch can fuse for you and where its rules stop. Next, we look at where PyTorch ends and CUDA-C begins. That is the layer beneath the framework and when you would reach for it.